Hey everybody, welcome to module number 4, Understanding ORP. Okay, in this module, we are going to be discussing what ORP stands for. Okay, what is oxidation? What is reduction? What are oxidation reduction reactions? Okay, ORP meter, and what is it measuring? ORP of different liquids, what is better for human consumption? Water with a positive or negative ORP? Examples of different ORP values. Okay, this module covering ORP is going to give you a basic understanding, okay, of what ORP is and ways that you can discuss ORP when you're doing a demo or when you're discussing the properties of the water with potential clients, or if you're trying to educate your downline, okay, who may have questions for you. You want to be able to give clear, simple answers that people will be able to understand and get the picture. Okay, so ORP stands for oxidation reduction potential, okay? Or another way you can say it is redox potential. Okay, so you're gonna need to know that off by heart. It's gonna be something you're gonna be saying frequently, and it's you know, it is very simple. Maybe at first it seems like a mouthful, but with practice and repetition, it's just gonna be automatic. Okay, so on this slide we have two pictures, and these are very simplistic representations of oxidation and reduction. Okay, so if you look at the top picture, we have two molecules, okay, and the red one has an arrow with a little yellow dot, which is supposed to be an electron, okay, and the electron is leaving the molecule, okay. So that is a oxidation process. That would be an example of oxidation, okay. And then we have the blue molecule, and you can see the arrow is pointing towards the molecule, and that is representing an electron being given, or that molecule is receiving an electron, okay? And that is an example of reduction, okay? And then if you look at the apple, so the apple was cut in half, it is starting to brown, it's aging, and that is because the molecules in the apple are losing electrons to the atmosphere, okay? So the apple is being oxidized, and the atmosphere is the reduction, okay? And oxidation is happening all the time. It's happening to everything at different rates, different things affect it, okay? So oxidation happens when a substance, molecule, or atom loses an electron, okay? Reduction happens when a substance, molecule, or atom gains an electron. This transfer of electrons is responsible for the oxidation on one and the reduction of another. So that's the oxidation reduction reaction. They always happen together. Okay, so when there's an oxidation half reaction, there's always a reduction half reaction. So they go hand in hand. So something will lose an electron, that will become oxidized, and something will receive that electron, and that will be reduced. Okay, so in simple ways, a reduction or reduced is the opposite of oxidation. A simple way to remember this is to use the term oil rig. Oil means oxidation is loss, and rig, reduction, is gain. So that's a little acronym that I've learned and I use and I share with people that are trying to explain this. remember oil rig, okay? Once again, oxidation is loss of electrons, okay, oil. Reduction is gain, okay? Gaining what? An electron. It's very simple to use, and it really is a helpful tip. When explaining this to someone, when explaining this information to someone new. These two half reactions are also called redox reactions. So that's a simplified way to say oxidation reduction reactions. You can say redox. These reactions are happening all around us and to us all the time, okay? So oxidation, okay, and reductions are happening all the time. Yeah, it is unavoidable. Okay, it is what is going on in the universe. It is the transfer of electrons. Okay, so some examples of oxidation I like to share with people during a demo or with clients is obviously the apple is a very simplistic way for people to get their grasp idea of oxidation. Okay, rusting. Okay, iron or steel that has been rusting. That's an example of oxidation. Okay, so the metal or the steel is losing electrons to the atmosphere or to a water. If it's rainwater, okay, or if it was as an example, okay, and those electrons are being transferred, and as a result, you end up with rust. Okay, that's the byproduct of oxidation. As another simple example would be firewood, okay, or a bonfire. So you're burning wood. You're speeding, by creating a fire, you're really ramping up that oxidation process, and electrons are leaving the wood, okay, entering the atmosphere. And as a byproduct of this oxidation process, you end up with ashes. Okay, and that's why ashes don't burn, because there's nothing left for them to burn. That's the byproduct. That's the leftover waste. Okay. Oxidation is the cause of the aging process. This happens when biomolecules, like the molecules found in cell membranes, okay, so every human cell, okay, has a layer around it called a cell membrane, and it's created by these things called phospholipids, okay, and they're like a fat, and that there's a layer of that around every cell, okay. So that's what I mean by cell membranes. As an example, are reacting with a reactive molecule, and there is an electron transfer taking place from the cell to the reactive molecule or free radical. The cellular biomolecule undergoes oxidation. So reactive oxygen species, or molecule free radicals, we can call them, which we're going to get into in another module. These types of molecules that are very reactive, okay, when they're in the body and they go unchecked, they can take electrons from the molecules of things like our cells, okay? And when that happens, our cells become oxidized. And when our cells become oxidized, okay, that can cause issues with the cell starting to break down, okay? So that's another example of oxidation. And lots of things that we're exposed to in this day and age will accelerate that oxidation process on our body, okay? So excess alcohol consumption, smoking, okay, recreational drugs, prescription medication, fast food, okay, heavy metals, okay, different pollutants in the atmosphere, okay, mental stress creates an acidic environment, or can create free radicals in the body. So all these things, okay, if we don't have the proper nutrition and the proper immune system and the proper amount of antioxidant production, these types of things can create a lot of oxidation in the body. And just like the apple, okay, or the piece of metal rusting, that starts to happen to our body. We start to age faster. We start to degenerate. Okay, so ORP meter and what is being measured, okay? Because when we do our demonstrations, we use the ORP meter and we show a distinct difference between bottled waters or beverages of different kinds, like vitamin waters or Gatorade, carbonated beverages, okay, including carbonated water, and the Kangen water. And there's a distinct difference. Obviously, the Kangen water, we end up with a negative ORP, and is usually the only one on the table that has that reading, okay? So ORP is similar to and is related to pH. Now, I wanted to throw that in there because pH has an effect on ORP, okay? So especially when we're producing ionized or electrolyzed reduced water, okay? The more negative ORP a substance has, the more alkaline it will be, okay? The more positive the ORP is, the more acidic it will be. And we can, so ORP and pH are very, very dependent, okay, on each other. And there's a direct relationship between the two. And ORP is affected by pH. The ORP meter is responding to oxidizing or reducing ion activity in the water. So if someone says, okay, well, what does that mean? Because I had one individual once ask me if that was measuring the conductivity of the water, is what he asked. He used to work for a filtration system, a water filtration company, okay? And he knew all about water pH, water chemistry, buffers, and he knew about making water, increasing water conductivity, okay? So he asked me if this was indicating a water's conductivity, and it's not. This is not measuring a water's conductivity. You could simply add salt to a water, and that would increase the conductivity, because you'd be increasing its electrolyte concentration. Okay, so what we're reading is the oxidizing or reducing ion activity in the water. Okay, so we're reading the redox reactions in a liquid. Okay, it measures a water's capacity for electron transfer. Okay, that's another way to put it. The meter represents this in terms of millivolts, thousandths of a volt. Example, 1,000 millivolts is the same as saying 1 volt. So the meter, the reading is in the millivolt units. Okay, so you're reading a potential difference between 2 points. Okay, that's what a voltage is. So when we're reading the ORP, we're reading a potential difference or a voltage potential or an electromotive force between 2 points. We're taking the difference between those points and it's giving us a reading, okay? If the reading is positive, it means that the difference between the 2 points, okay, is oxidizing. It's an oxidizing environment, okay? It has a positive polarity. If the reading between the 2 points is negative, okay, it means we have a reducing or an anti-oxidizing environment, okay? The meter does this by measuring the potential difference between a reference electrode in the probe that has a fixed value and the probe that is in the solution. The probe looks like one electrode, but there is 2 within the probe. So if you see the probe on the picture, okay, that's a long blue plastic piece. On the tip of it, okay, there's a metal sensor. Okay, and these are normally noble metals like platinum or gold, okay? And inside that plastic piece, there's a second electrode that is isolated from the liquid and is it never makes contact with the liquid, okay? It's isolated from everything. So you essentially have, in that one looking probe, there's actually two probes, okay? So there's the reference electrode that never changes its value, okay? And then you have the second electrode, which makes contact with the solution you're testing, okay? And this one obviously will fluctuate depending on the solution, okay? So as the solution's pH, okay, or what is in the water, if it's creating more oxidation or reduction, is going to change this value, is going to change what this is. And what we're measuring on an ORP meter, okay, is not the voltage of the liquid, but we're measuring the voltage between the two electrodes, okay? And that's indicating if a substance is promoting oxidation or promoting reduction, okay? And we want to be basically, in the simplest form, not things that are beneficial for your health, okay, or that are not gonna add to or increase the oxidation process, will be negative or will be a reducing agent, okay? So that's what we're representing here with ORP. Keep in mind, the ORP meters, okay, need to be calibrated, and you will not give true representations or true real specific measurements if they're not calibrated, okay? So one of the ways I calibrate my meter before a demo is I will generate 2.5 hypochlorous acid and 11.5 strong Kangen water from my Kangen device, okay, in 2 separate cups, and I will dip the probe in the 2.5 and let the meter read that until I can get it as high as possible. So because it's 2.5, it's very oxidizing. It's going to, I usually get it up to about a positive 1100, 1150, sometimes even to 1200. And then I'll put it in the 11.5, and I'll usually get around negative 870. Okay, and I'll go back and forth, and that is going to generate a span for my meter to read. Okay, so calibrating your device, your ORP meter, before your demonstrations is necessary and is crucial. This millivolt reading will appear either positive or negative. Okay, so we already went through that. Now, the meter doesn't have a positive sign that pops up. If it doesn't have a negative sign, it means positive. There will be a little negative indication symbol that will pop up on the screen if you are measuring a reducing agent. The measurement indicated on the meter in any given liquid represents the total oxidation and reduction reactions happening in the liquid and/or. Okay? So if when the probe is in the liquid, the more, if you're reading a negative reading, so the substance is showing that it has a negative ORP, what is happening is there's electrons being transferred to the probe. Okay, so between the two, this one's more negative than this one. So when you take the difference, you end up with a negative number. So this minus this gives you a negative number. If you put the probe in an oxidizing liquid, okay, electrons will be taken, okay, and when you take the difference between the two, you get a positive number, okay? So another simple way to explain it to people when you're doing your demonstrations is simply saying the more positive a number reads, the more oxidizing the liquid is. Okay, the better it is at oxidizing your body. Okay, the more negative a number is, okay, that's an indication that it has the ability to reduce oxidation, or is the opposite of oxidation, which means you are not, by drinking this type of water, you are not adding to or in any way speeding up the oxidation process. Okay, and then another example I like to use is I will say positive readings are electron stealers, okay, because they want to be reduced. So they will take electrons so that they can be reduced. And negative liquids are electron donors, okay? So positive electron stealers, negative electron donors. The more positive, the better at stealing the electrons. More negative, the better at sharing the electrons, okay? So good. So if positive, this indicates an oxidizing environment. And if negative, it indicates a reducing environment. So that's the simplest way I can come up with, guys, without getting to, you know, without getting into equations. Okay, that's the simplest way that I can put it. Okay, so we all know this scale. Okay, and if you don't, you're gonna know it. This is the ORP scale, and when you're doing your demonstration, when you're doing the ORP section of your demonstration, you want to have this up in some way. So there's a few different ways that I have done it and recommend. One is you create a PowerPoint, and you either have a PowerPoint on a flat screen TV or on a projector behind you while you're doing your demonstration. This is in the ORP section. Okay, and in this section, when you're doing the ORP section, you should also use this when you're talking about oxidation and reduction, and you're showing the differences. This will lead into the antioxidant topic or a section of your demonstration. Okay, so there are a few ways you can do this. Like I said, PowerPoint. Depending on if you have a larger room of people, that's always the best way to go. Okay. Another thing you can do is get a what are those things called? Like those 3-ring paper stands. Okay, but you can get like pictures made on them, and you can fold them over. That's another way for smaller groups. And another thing that I've created is I actually have a set of binders that I had made. I had made a binder with the pH scale, the ORP scale, okay, showing the oxidation reduction reactions, showing you know, the human body in different percentages of water in the different organs. Okay, and then what I've done in the past, especially for smaller groups of 1 to 3 people, I will actually have them hold the binder. Okay, each one will get a binder, and I'll get them to flip to this page, and they can look at this with me while I'm doing the oxidation tests on the liquids. Okay, and I simply just explain to them that this is an oxidation or antioxidation scale, and the more positive a substance is, the more it promotes oxidation. So that means, we now know that means rusting, okay, aging, okay, which leads to sickness. So examples are the bottled waters, tap water, sodas, okay? And when a substance or liquid is negative, it shows that it is a reducing agent, okay, and that it promotes antioxidation. So we have vitamin C, green tea, okay, cod liver oil, and then we got the Kangen water on the far left, okay. And as you explain this, you will say that the more negative something is, okay, the better it is at donating electrons, okay. So once again, electron stealers on the left, on the positive, electron donors on the right. Okay. One thing to keep in mind is the scale is logarithmic as well, just like the pH scale. Every time you increase, so let's say you go from 0 to 100 or 0 to negative 100, that is 6.9 times more negative. Okay, so from 0 to negative 200 is 6.9 times 6.9. Okay, so let's say green tea, you have negative 100 and you got Kangen water at negative 400. Well, the negative 400 is 6.9 times 6.9 times 6.9 times more negative than the green tea. Okay, so that's what the meter is representing. Each whole value increase or decrease is a value multiple of 6.9. And like I said, this is related to the pH scale. So if you look in the middle, you got 0. That would indicate perfect H2O distilled water. Okay, nothing in it at all. So you would have pH is 7, and that would read 0 millivolts. It wouldn't be oxidized, it wouldn't be reduced. It would be 0 millivolts. So the more positive we get, the more acidic. The more negative we get, the more alkaline. So they're very similar. Okay, what should the ORP be of optimal drinking water? Okay, if you guessed negative, you're right. Okay, if you guessed negative oxidation reduction potential, you are right. Because water with a negative ORP is a reducing water. It does not steal electrons from the body when consumed. Reducing waters will not oxidize the body's cells. Oxidizing waters, or waters that have a positive ORP, when consumed, can and will react with the body's cells and take electrons in order for it to be reduced. The more oxidizing water you drink, the greater the potential to increase oxidation of the body. So that's pretty important information, and I like to share that with people when I'm doing my demos, because a lot of people drink tap water. A lot of people live off bottled waters, and a lot of people who are, especially that are health conscious, they consume a lot of water. Okay, so when you drink waters or beverages that are positively that have a positive ORP, okay, they want to be reduced. Everything's looking for equilibrium. So the positive things want to they want to steal the electrons, okay, so they can become equal, and the negative things want to give away electrons so they can become equal. So everything's looking for equilibrium. So when you put these oxidizing beverages in your body, they do become reduced. They do take electrons, and this is happening from your body. So for people, especially people that say, I already drink a lot of water. Oh, I already drink a lot of alkaline water. Well, what you can demonstrate in your demonstrations is put alkaline waters in your rows in your demonstration. Put alkaline water in there to show that Just because the water is alkaline and was made alkaline by adding alkaline minerals, it still is oxidizing, which means it still promotes oxidation, which means it still actually has a more of an acidic effect on the body. Okay? So for people who, like I said, are very health conscious and they, oh, I already drink a lot of water, I'm already drinking 3 to 4 liters a day, and tell them to bring their water to your demo and you can test their water for them. You can show them how oxidizing the water they normally drink is if they don't already drink tap water. Okay, so the more water people drink, the more water they drink, the more that this water needs to be reduced. And it's fact that the water will take electrons from the body. Okay, like from for an example, from your cells. Okay, so you're drinking water to hydrate and for health, yet you're putting something in your body that is using your energy to reduce itself. Whereas if you're drinking a water that has a negative ORP already, we can call it living water, it puts electrons in your body. So you're drinking something that doesn't require a need to be reduced. It will actually give away electrons in your body to other things that may be harmful or may need to be reduced. Okay, and then the more you drink this water, and for the longer, the better the effect will be on your health over time. Okay, examples of different redox couples. Okay, so I also like to give people examples of where else, because a lot of times for some people, this is the first time they've ever seen an ORP meter or they've even ever heard of it. So I like to give people examples so that they can relate to it. It doesn't seem so foreign after that. All the internal fluids in the body have a negative redox couple. Okay, so that's very important. Not a coincidence. Okay, I don't think the body would last or be able to live very long if the fluids in the body had a positive ORP. Okay, there's a reason that the liquids in our body, all the fluids in our body, have a negative ORP. Okay, that is an environment that is an electron donating environment. It's an environment that is, for the most part, not acidic, and it is an environment that will be able to promote life, promote growth. Okay, amniotic fluid surrounding a baby, cerebral spinal fluid. Okay, that includes the fluid around your brain. Okay, between your brain and your skull. The internal environment of a healthy cell. Okay, the internal environment of a healthy cell has a redox of negative 20 to 25 millivolts, and that actually directly relates to a pH of around 7.3 to 7.4. Okay, and here's a little tip, little fun fact. When a cell, okay, wants to split, okay, to produce another cell, or when a cell needs to heal. So if you've damaged cells, let's say you've hit your thumb with a hammer and it's throbbing, so now you've got a whole bunch of damaged cells, okay, or you bruised yourself, or you got an area with damaged cells. For cells to split, okay, or for cells to heal, the energy in that cell, okay, has to increase in well, let's say it has to become more negative to around negative 50 millivolts. So at negative 50 millivolts of the internal environment of a cell, okay, in order for it to split, or to heal, so in order for it to produce new cells or to heal itself, it needs to increase the power to negative 50 millivolts, which actually would relate to a higher pH, okay? So these are some examples of parts in the body that have a negative ORP, okay? Human blood has a negative ORP, your saliva. I thought this was really interesting. A woman's breast milk has a negative ORP of around negative 70 to negative 75 millivolts. So right from birth, the food source for a newborn is a reducing agent liquid. Okay, to me that's incredible. It's a living liquid. It puts it's an electron donating liquid, and it does not allow oxidation. It is an antioxidative environment. I think that's very interesting because a lot of mothers that are not able to breastfeed or choose not to breastfeed, what happens is we're actually using this synthetic milk with tap water, and from an oxidation reduction potential perspective, it's the complete opposite of breast milk. It is very oxidizing. You're using tap water, and tap water has a high ORP, and it can be anywhere from 3 to 500, and then you're putting the Emphalac in for the simulated milk, and now you're giving your baby something that is oxidizing. So I'm not saying don't do it. I'm not saying it's bad. I'm just saying from an ORP perspective, it is a big difference between breast milk and simulated milk products. Okay. So there's a lot of examples in the human body of things that have a negative ORP. Now keep in mind, there are substances out there. So just because something has a negative ORP doesn't necessarily mean it's not harmful to the body. Okay? There are certain metals or substances that you can dissolve in water that can make the water a reducing agent. Okay? It doesn't mean that it would be safe for your body to consume. But now getting that out of the way, reducing agents, a water with a negative ORP is more compatible with the body, okay? Regeneration and growth would not be possible in an oxidizing environment. That's pretty self-explanatory. If an environment is oxidizing, okay, electrons are being stolen. Okay, electrons are being stolen. So how could something grow in an environment where the electrons are being stripped from it? Water for supporting aquatic life must not have a redox above 300. Okay, so that's pretty interesting. So if you have a fish tank, okay, for an example, if the water becomes above 300 millivolts, it'll be too oxidizing for the aquatic life. Municipal tap water sources are around 400. Swimming pools, hot tubs, are 600 to 750. So disinfected water. This is another way you can explain to people where they might see or where ORP is used in the world. Okay, so for an example, maintenance employees at a hotel or at a public swimming facility will check ORP of these swimming pools, and they usually want it somewhere between around 6 to 750. When they get that ORP reading, they know that the water is disinfected and that germs, bugs, and pathogens for the most part are going to be killed in the water. Especially public swimming pools, people are kids pissing in it, blowing their noses. Okay, some kid might take a dump in the pool. Okay, you don't want people getting sick. Okay, people go in with open sores. When water is above 800 or above, it starts to become sterilized. Okay, that's another example. So water within. So this is just showing you that the higher the ORP gets, the more oxidizing the water becomes. Hypochlorous acid produces positive 1,150 millivolts. This is what makes it special, not the pH. Keep this in mind. This is how you can explain to people the difference between the Kangen units 2.5 hypochlorous acid and the 2.5 from any other ionizer, commercial or residential ionizer out there. Another way to put it is even soda has a pH of 2.5. But the ORP is only around, could be anywhere from 300 to 400. So soda is not gonna, or Coca-Cola or Sprite's not gonna kill E. coli or Salmonella or MRSA. But so it's not the pH necessarily, but it's the ORP that makes it so amazing at sterilizing. So when you get to that high number of over 1,000, 1,100, this liquid is very oxidizing. Little bugs, pathogens, germs, viruses, funguses, they are having the electrons stripped from them at a very rapid rate. Okay, so that's all we have here for ORP, oxidation reduction potential. So just keep in mind, remember what it's measuring. It's measuring between the two electrodes, the reference electrode and the electrode in the substance, okay? Remember oil rig, so oxidation is loss, reduction is gain, okay? And keep in mind when you're explaining this or using, when you're in this section of the demo you're going to be doing, or explaining this to a potential new client, or answering any questions of your downline, you want to be able to make it as simple as possible so that they can grasp the information and really absorb it. Okay, so like I said, that's it for ORP, and I'll catch you guys on the next module.